Oh, it just smoked. Well, I just killed this fan. Hi, Dylan. Hello and welcome to Sealio's Projects. Today we're going to go through all the different fans you might see in the wild, from computer fans to refrigerator fans, and to even fans that run off of 230 volts. So, to start off, we're going to use just one of these tiny little mini fans. You might find them in power supplies, you might find them in old graphics cards, but they usually operate off of 5 volts. And all you need to do is just plug in a DC source. As long as it's within somewhat range, you should be fine. So as you can see with this power supply, it's fixed to 1 amp, at least on this end. It spins not too great, not too little, and yeah, it's very basic. They usually break very easily, which is why you don't find them in high-end stuff like graphics cards and computers. So that's just the first one. Now, we just need to swap this back to 12 volts. So for the normal computer fans, they're going to be operating at a little bit of a lesser voltage, lesser current, because this is a fixed 1 amp. Then when we get to the big ones, we're going to have to switch over here because that will allow me to do 24 volts. So now we get to our next one, which I've yet to strip the wires for, so we're actually going to do that right now. This is a 12 volt DC fan that I'm pretty sure I pulled out of a power supply, a 12 volt power supply. So these, they're just very standard. They're in more cheaper power supplies because of the fact that it only has 2 terminals, so they're a little bit cheaper to produce compared to more 3 or 4 terminal ones like you see here. So as you can see, they're pretty good. They're quiet-ish, but they still make some amount of noise. They're not nearly as loud as, well, I guess, one that you'd plug into 230 volts, but they're still pretty good. And they're for power supplies, which very often don't really use the fan inside them, but yeah, so they're pretty good. Put that on the ground. Next, you get a modern day blower type. This is made by Foxconn, like a solid majority of the fans that I have. And it's 12 volts, 0.75 amps. And this, I'm fairly sure I pulled out of a mini PC. Now these, as you can see, have 4 wires, which means they have 4 poles. And yeah, they essentially suck in air from the top here, and through these fans, or through these blades, they push air out, which is perfect for PCs when you need to get more hot air out. But granted, always remember, you always want more positive pressure instead of negative pressure in a PC, because positive pressure will also just push out the air. Negative pressure will leave a vacuum, which might not be something that you want. So, just having to plug this back in. Oh, and also, most to all computer fans will operate at 12 volts, just because you require less current. Because if you have a 5 volt fan, you want it to act the same as a 12 volt fan, you're going to have to pull more current, which might not be the best thing that you want to do. Because voltage is a lot easier to supply than current when you have to deal with things like massive power supplies and massive graphics cards and CPUs. So ground to ground. I'm using just a very standard DuPont connector. Wow, that actually has a lot of push. So the air, obviously you can't feel it, but the air is actually coming just straight out. So, as you can see, it blows pretty darn well. But since it is still plastic, it is still good. It's But this is mostly for CPU fans. Essentially the CPU, don't want to short that, will be mounted like this, and then it'll just blow straight out. They're great. The only problem is, though, they're a little bit harder to clean, and taking them apart can be a problem. And usually they're more prone to breaking than any of just the standard fans. So, without doing anything bad. But yeah, these are pretty cool. They're also super useful just as extractor fans because you don't have to stick the extractor here. You can stick them right here, which makes it a lot smaller and, well, they're a lot thinner. So having a thin extractor, while it's a lot less surface area, they're a lot more portable. Also, they're perfect for making on-the-go fans. Now we get to a much larger version. This I pulled off of a much smaller, or a much older CPU. It is covered in a lot of dust. This is a 12 volt, 1.35 amp blower compared to a 0.75 amp blower, so this is nearly double the current, so it should be a lot louder. And this is for when computers essentially had 1 or 2 fans. This, in the case, was actually the only one fan. This is a 3-wire thing, and as you can just see, it's yellowed and it's old. I don't even recognize the company that it's from. So, we're gonna take it and plug it in. And fun fact, I actually got this power supply out of the garbage. Huh. That's odd. It's, oh. So I was wondering why it wasn't spinning as fast. I don't know if you can see that. It's not spinning as fast. The reason why is because this is not operating at the correct current. So what we're gonna do right now is we're gonna do some switching up. We're gonna go here. We're gonna set it to about 12 volts. We're gonna make sure that it is 12 volts using this multimeter. And so let's see. Okay, so we're about 3 volts. Almost there. All right, so we are at about 12 volts. Close enough with a little bit of voltage sag. So, thankfully, since it's common ground on both terminals, I don't even need to change the ground. I just needed to change the positive. So, with this, we're gonna see, hopefully, how well this works. Red is positive. No, it's so weird. It's also pulling minimal current. Whatever. Do I have to switch this? Okay, so if I up the current, or if I up the voltage, it makes it a little bit more. So let's see, what voltage are we running at? It doesn't know, but I'm gonna stop running it at that voltage. So this, I can tell you from experience, oh, okay, something disconnected. I thought the thing just exploded. This fan can be very, very, very loud. If I were to hook this up to a 12 volt power supply, not a variable power supply, it is very, very loud. There's a reason why I took this out of the case. Now we get to our standard type of fan. You're probably gonna find this type of fan in free cases, or this type of, essentially, this is the fan that you get for free. This is a Cooler Master fan, which they're pretty good. They're not Noctua, but they are still pretty good fans. They're quiet enough, and they are very strong. They're not slow. And now we also have to play the fun game of which one is the negative, or which one's the positive. So let's just plug this one in first. And oh, ooh, that was something. There you go. So as you can hear, it's pretty quiet. It does enough, which this is also, oh, that's why it's operating a little bit weird. This was negative, so that's weird. They're all operating on them. Huh, that's weird. I think we'll keep it on there just for safety. But they're pretty quiet, and they work fairly well. This one is from 2021. And this is 12 volts, 0.16 amps. So that's about 1.2 watt fan. Nothing really much compared to a 240 watt fan, which we'll get to at the very end. So, all right. Oh, and by the way, usually, if you have a fan, whichever side has the grate on it is the side that it will blow out. You can also sometimes find it on, what do you call it? You can sometimes also find it on markings, like right here. See if I can show it to the camera. As you can see, it blows out a certain way. So it blows out down, and the blade rotates to the, well, in this case, to the left, which also can be seen by the fact that the grate is on this side. But we'll get to that in a second. This is a big Foxconn fan. Like I said before, with the other Foxconn fans, they're pretty big. They're fairly standard. Now I have 2 of these on the top of my computer case because these were old CPU fans, which means these things used to rip. This is a 12 volt, 0.9 amps. So if you dump in a lot of current into it, you can get a pretty good positive pressure input, which when you have a 3080 and a 12700K running in a PC, and you're playing very high games, or very high power games, you need something like this. Also, these were free, so compared to these Noctua fans, which they can be like $20 to $30 sometimes, pulling these out of a PC case, as long as you don't mind a little bit of extra noise, these are pretty sick. And usually you can get them for free, or for stupid cheap. They're also 4-wire fans, so if you care just to do a tiny bit of, just pulling out the wires and fix them, they will usually act perfectly fine. See, as you can see, it's a, oh, that's weird. Uh-oh. Why did it just stop? Oh, it just smoked. Well, I just killed this fan. Hi, Dylan. Okay, I just killed this fan. Well, that's why you don't run fans at an incorrect voltage. Oh yeah, that's dead. Okay, well, I guess we're gonna skip past that fan. And we're also gonna stick to the 12 volts instead of the other volts. Yikes, wow, no, okay. Well, I got that straight on camera. Usually these are much better. I was able to run one of these at 20 volts once. Maybe it was the current? I don't know. Well, you just got to witness me killing a fan. It's the first time I've actually ever done that. Usually it's the power supply that's doing it on its own. Yeah, no, that's dead. Well. Alright, let's make sure not to kill the Let's make sure not to kill... Okay. Let's make sure not to kill this expensive fan. This is a Noctua fan. They are very quiet. This was supposed to go to a CPU cooler, an NHD15, I'm pretty sure. This was just a spare because we couldn't fit the other fan in the case. So, yeah, so we have this. So, we're going to wire this up, and if this fan blows up, I'm going to cry. So, here we go. And I think we're going to try with the yellow. Okay, not on fire. So it's a lot quieter and a lot more surface area. It doesn't blow as much, which we're gonna keep it at that just because there's no way in hell I'm plugging it in to that again, because if I blow up this fan, I don't think my oh, why? Okay, I thought it blew it up again and it just shorted the power supply. Okay, that's fine. But as you can see, they're pretty quiet and they're pretty good. I mean, they're expensive for a reason. They're expensive because at high RPM, they're very quiet. You'll probably not really find these in the wild, per se, compared to like these just old fans, including the one I just blew up. But they're pretty good, and if you can get your hands on them, keep them, because they're perfect for really anything. Alright. Now, this is a fan that I actually can't show you how well it works because I don't have a 230 volt power supply, but this is a solid metal 230 volt fan given to me by my uncle. This can take off fingers, I know, because he took a carrot and put it into one of these. Now, I'm not going to show you with this, I'm going to show you with this one how it would act against a popsicle stick. But yeah, they're fairly cheap, not really expensive, but when they spin, they spin. They're mostly for... machinery is the best way to say it, because realistically you're not pulling 230 volts unless you're in a different country besides the US, but my uncle uses a bunch of these for cooling. He made a oven that actually was used to bend stone, which is pretty cool. So now we get to this type of fan, which it looks like a normal computer fan. It's about the same size, but there's one tiny difference. It plugs into the wall, which it's very great, except for the fact that it's a little bit sketchy. Oh, it also unplugs. Okay then. Yeah, it just has little 2-pronged terminals on the back. So, I pulled this fan out of the garbage because they said it didn't work. I hit it with... Oh, I hope you can plug back in. I hit it with a little bit of grease, and the thing works perfectly fine. So let's plug this bad boy in. So it's a little bit loud, as you could probably guess, but it's fairly strong. I mean, it's not as strong as what that fan should have been. I still can't believe I blew that up. But yeah, it's also a little bit loud, but honestly, for something on the go, or for an extractor fan, this would be perfect, because unlike with something else, you don't need an extra power supply that's gonna convert wall power to DC. So this is perfect for that type of stuff. Oh, it smells like burnt plastic. My mom's gonna be mad at me. So let's unplug that. I don't know how expensive these are. I couldn't really find it online what this would be. So yeah, but these are something like this. It's pretty cool. Again, you won't really find this in a computer, but if you're going around a garbage site or something like that, you might just find these just lying around. And now we get to my favorite. The reason why we needed this power supply in the first place. This is a... Oh, I kept saying it was 240 watt. It's not. I think I was able to dump 10 amps through this. I don't think I'm gonna repeat it after what just happened, but this is a $230 fan, which is very insane. I got it off of an industrial freezer. Now, the blades on this are plastic, but the metal casing is, oh well, it's metal. So what I'm gonna do first is we're going to make sure that this is 24 volts. We're at currently 4.56. Uh-oh. Huh. Okay, so we didn't blow a fuse. Thankfully, something was wrong, which is probably why this thing ended up in the garbage, because it just decided to not do more than 1 volt. So, okay. Back to what I was saying before. We get to do the fun thing, which is use this big boy. So we're just going to put this to 24 volts. 19, 21, 22, 24 volts. Which means that this is all good to go. Just need to plug it in and be very, very safe about this. So we have our positive connected. We have our negative connected, and for what you've all been waiting for. Oh, I'm gonna have to hold this in, aren't I? Yep. Okay. Uh-oh. Okay. Alright, well. We have life. Oh god. So, to say that this is a strong fan, just watch this. So this is very, very strong. Jesus. So, I'm gonna take this, and we're just gonna put it on here and see what it does. Never mind, I actually want to keep this fan, so we're not gonna do that. But this is a very, very strong fan. I mean, just, how many fans do you know that can propel itself? Not into the cutter. So, yeah. This is a very strong fan. It definitely lives up to its $230 name. But yeah, it's really strong. Again, I pulled this off of a cooling unit for an industrial freezer. So not the freezer itself, the thing that cools the freezer. So yeah, it's absolutely insane. I do not want to put my fingers anywhere near this while it's operating because as you can see, I've already sliced my hand up a little bit yesterday while I was cooking. So yeah, I'm trying to think if there's any really other fans. No, I mean I would have really loved to show you guys this because it did operate at some point. I don't really have a supply that could do this that I trust would not burn down my house. But yeah, well, I'll see you next week. Thank you so much for watching and have a great day. Hello, welcome to Sealio's Projects. Today we're going to use some aluminum foil to make a Faraday cage to see if it can actually block AM and FM radio signals on different types of radios. Really old radios, sort of modern-ish radios, and automatic scanning radios that you just press a button and it automatically finds the channel. So, the first thing we're going to do is we're going to make the Faraday cage. Originally, I was planning to use aluminum foil and cardboard and plastic just to make an actual box, but I don't have cardboard or plastic, so I'm just going to make it out of aluminum. So alright, so we've made our so-called box. It's not the greatest, but it should do. So, you might wonder how we're going to get the signal, or at least the audio, out of this. Well, first, we're going to start outside of it, and then we're going to use a spider plus an aux cord to plug straight into the headphone output, which will allow us to have the radio inside of the box with audio still coming out. Now we're also going to just cut a door for it. That should be enough. Okay. So we're going to put that there. We're going to open the antenna. Going to turn it on. Now this is a very old radio. My great-grandfather had it. So now we're going to turn on this. Now the cool thing about this is that the audio, when it comes out, it'll create what do you call it? Plumes of water. So right now we are on AM radio, also known as amplitude modulated. Alright, so we got something. You can sort of hear it. So, obviously, you can hear it. You can still hear it without the antenna. You can still hear it, and now let's see. So fully encapsulated in tin foil, you can still get through. Now this might be because AM radio has some different signals than FM properties than FM radio. So we're gonna go to FM. Let's see if we can find anything. Maybe not. All right. Well, I guess we now know that this type of radio actually does survive. It does work. All right. Now we're going to try this radio, which was supposed to be the one that was going to be this one, but this is one from the 1980s. This one was from the 1950s, or at least to my knowledge. So this should be able to pick up a lot better signal. I mean, when I tested it yesterday, it was a heck of a lot better. So, starting with FM, starting with AM. Found the same station. That's insane. Okay, so we got something. We're gonna see, as you can see, you can hear it. Nothing. I didn't even have to put the top on.
I'm trying to do that. I don't know if they want to.
I don't even need a top for that. That's insane. So as you can see, it's still getting some signal, which shows that the radio is still working, but
It's right at check for 500.
That's it. And I feel like the reason why it works is because this has an external antenna, this has an internal antenna. So as soon as I put it in there, it's blocking everything. I guess it's just so much antenna that it's being offset. So now we're gonna go to FM and see if it does the same. Alright, we got a signal. Alright, so, you can hear it, you can see it. Alright, so, it works with it in. Yeah. FM radio goes right through. The AM radio doesn't. That's crazy. So we know that this does block AM radio, at least on this. So now we're going to go to the newest type of radio, which I realize now does not have an audio out. So you're just gonna have to hear it, I guess. So this uses an auto scanning function.
And you say it's not just the drugs trade; it's organised crime more widely. What other crimes are we talking about?
Auto radio. Okay. So we have this. Let's see. We still have it. It's gone. Take it out.
What are these organised crimes trying to do? Is it simply about eliminating candidates that they fear?
Okay. And then nothing. So it blocks AM radio, does not block FM radio, and if it has a massive antenna, it doesn't really end up doing much, which that's a bit odd. Maybe it's just because of the fact that it didn't pick up any AM signal for some reason, because this is an older type of antenna module, so I wouldn't be surprised. So
that one to have certain politicians.
It works. Now, let's actually see if I press scan, if it will still find a signal, because it might just not be receiving that signal. Nothing. It doesn't find. So this does work with AM radio and essentially any amplitude modulated signal. Now, just a quick thing for AM and FM radio. AM radio is amplitude modulated. It's a much easier. That's a plane. So AM radio, or amplitude modulated radio, has been around for a lot longer due to the fact that mathematically it's very easy. All you need to do is have a signal of the same frequency with different amplitudes, which means different maximas and minimas. So it's very easy to do. Frequency modulated is where you have signals with the same amplitude, so same maxima and minima, but the pulses within, or the waves actually within there, are at different rates than the carrier wave, which a carrier wave is a base wave that does not change no matter what, and that allows the different antennas, or in the modules, to differentiate between what's just static or what's actual music. So that's also how these, I gotta turn this off, how these scanner modules work. If it doesn't detect something, if it does detect something that's different than the base signal, or the base signal, it will then display. Now it could just be static because of interference, or it could be actual music. So yeah, I do remember correctly that the person who technically invented AM radio was Reginald Fessenden, I think I'm saying his name right, and he was a Canadian-born inventor, and it was really cool the type of stuff that he was able to do. Now, some of the payoffs between, or some of the good stuff about AM radio is that it travels very far, requires very cheap materials to do so, and it can travel through majority of materials except water, metal, and really concrete. But if you're anywhere in the world and you go out into an open field, you can get AM radio. There are some AM radio stations that you can hear from another country, and it's really cool. But yeah, the only problem is though, they're more often at lower quality, and they require a lot more power to produce. It sort of depends, only because a stronger AM radio could require just a tiny bit more power compared to FM, because FM is more digital manipulation than physical manipulation, or at least that's how it used to be in the old days. So by contrast, FM radio, not as great at receiving. You need to be really close to the station, but in turn you get higher quality. Personally, if I'm stuck in the wilderness and I have to listen to music or hear any emergency stuff, I would much rather have AM radio than FM, because at least with AM radio, you're gonna know where to go, instead of FM radio where you'll hear the static in a lot clearer tone. So, yeah, alright, this was a part 1 of 2, surprisingly enough, if you're still watching. And in the next video, we're going to see if this box, if this Faraday cage technically, works with Bluetooth signals, which would be very interesting to see, because in a lot of movies people say, oh, just put your phone in a bag, or in a chip bag, it'll block the frequency. So we're gonna see if that could block against Bluetooth stuff. So thank you for watching. See you in part 2. Let's see, did we also lose connection on the Apple Watch? It disconnected. Hello and welcome to Sealio's Projects. This is part 2 of the Faraday cage versus radios and Bluetooth speakers. So, in this we're going to see if this Faraday cage with a little bit of a top on it, which is literally just some aluminum foil that's crumpled up, can block Bluetooth signals. In movies you see that people do it to block anything from connecting to their device, and with things like AirTags nowadays working with Bluetooth, you could see if putting your phone in just a cheap thing of aluminum will actually work. So first thing we have connected to is this Bluetooth speaker that's great for connecting wireless headphones to your computer wirelessly. I actually love this thing a huge amount. And right now we have it connected using the same spider, which is just a weird aux splitter like last time, to the Bluetooth speaker, which we also will be testing. So this one we're actually going to put inside of the aluminum foil. This one we're actually going to put inside of the aluminum foil, and this one we're actually going to put the phone inside and see how it works. Also, we'll be able to see because if my Apple Watch doesn't connect. So we're going to play the music. Okay, so I think that I paused it. Okay, I skipped the song. Whoops. So. Okay, so by the look of it, tinfoil does not work on the cheap transmitter. Now, for the even cheaper Bluetooth speaker. So, thankfully, all I need to do is just take this. I love how that works. And change which thing we're outputting to. So, you can still hear it. It's not as great. I'm actually gonna take this apart in a later video. So, gonna make it nice and loud. Interesting. Wait, what? You heard it stop for a second. It actually is working. What the heck? You can hear the signal actually breaking up. That's it. So it actually does work. Wait, so then why did it work with... You see how it's cutting in intermittently? So if I make sure that nothing, like there's no holes, it actually does block it. So it does work. It actually does work. Oh, that's awesome. Because the buttons and to control it are all on this side, so I'm not even squishing on the buttons to pause it. And as you can hear, I'm not pausing it and stopping it. It's actually cutting out intermittently. I bet you good money that this is gonna get copyrighted, so hope you like the video. So, we know that it does actually work. So it does work. It just so happens that this $5 adapter is better than this apparently like $13 speaker. So that's interesting. Okay, so now we're gonna turn both these off. Alright. Now both of these are off. Now we're gonna see if what happens, we're gonna see what happens if you put the actual. Oh, did it? Oh, it already connected. Well, that makes life easier. We're gonna see what happens when you put the actual phone inside of the tinfoil, like what people do in the movies. So, the song, by the way, is Laserhawk. Or sorry, the song's "Overdrive" by Laserhawk. Great, great song to listen to. So we have it in the first layer. This is the last thing we're testing. Might as well go crazy. Let's see. Did we also lose connection on the Apple Watch? It disconnected. It straight up disconnected. The Apple Watch is still connected. Let's see if I can ping. Okay, so it cut off and straight up disconnected from the speaker. Now granted, this is a cheap speaker. I don't have any super expensive speakers because I like headphones. So, actually speaking of headphones, nah, I left them upstairs. So, that's crazy. So now, let's see, if I unwrap it, will it automatically connect like it did before? Oh, my phone's not scratched. So if I take it out, that's so cool. So, we found out that, yes, it connected. Okay. So, we found out that aluminum foil can actually block Bluetooth signals. Apparently, really cheap ones, I guess it's just a bet on how the antenna is made. So, it worked with this. And the phone was actually able to block it with this, or the tin foil was able to be, aluminum foil, sorry, was able to block the phone from outputting stuff, but not to the Apple Watch, which I guess it does help the idea of that it's the antenna inside of the actual module. That's the reason why it's so weak. So, yeah, that's really cool to find out, the fact that it still does work just by, what do you call it, the same idea of why AM radio gets blocked, which is the fact that when you're sending out a signal, a Bluetooth signal, it still is some sort of wavelength. And items like metal and, well, let's just stick with metal. Metal is a very good conductor. And the reason why Faraday cage works is that it intercepts that signal and dissipates it through the material. Granted, there's a whole lot of stuff with Gauss's law, Maxwell's equations, and I took ECE 603 and 602, so it's pretty painful to explain it mathematically wise, but there is actual reasoning and understanding of why it works. And also has to deal with magnetic fields, which is really, really cool. Oh, and also Faraday's law. Forgot about that. So, yeah, so there actually is math behind this explaining how to do it. I don't know how to do that yet, but I do understand the reasonings why. So, yeah, if you're still watching, thank you for watching. This is really cool, and I'll see you in the next video. Hello, welcome to Sealio's Projects. Today we're going to be desoldering non-hot swappable mechanical keyboards using a soldering iron and a solder sucker to harvest the key switches that are on these keyboards. The key switches on these keyboards are blue MX switches, which I'd like to harvest just because I have a different project that I'd like to use them on. These keyboards are also not super special. They're cheap keyboards that you can get like the dollar store. So I thought, what better to harvest the key switches? So I'm going to be using a soldering iron and a solder sucker, as previously mentioned. I'm going to go through each one of these and take off all the keys, and yeah, it's going to be a fun project for the day that I got nothing going on. So the first step in doing all this is to take off the keycaps, which I'm going to do in a time lapse to save you some time. so we now have both keyboards taken care of, and now we get to dismantle it and desolder it. Alright, so with both keyboards taken apart for everything except these switches, we're now going to heat up the soldering iron, get the solder sucker ready, and take off every single one of these key switches. So, alright, let's do it. Alright, so we now have both keyboards fully unsoldered. My thumb and my hand are killing me. So now all I gotta do is just pop each one of these out from the back, because I don't have a keycap puller. And yeah, we'll see how many are still good. Alright, so we're finally done. We have all of the keycaps from these two, well, what used to be keyboards. We actually have the boards of the keyboards, which in certain ways you could actually use these still and just do some finicky stuff with them. Like, for example, if you just want to have a keyboard that just has the letter A on them, you could easily do that. But overall, we were able to harvest every single key from these boards. So there could be, I think, so that would be 216 if they're both 108 key keyboards. So these are 216 free keycaps, which, I mean, they're just buttons, so you can use them for whatever you want. If you want to use them on a Raspberry Pi to turn it on and off, it works perfectly. And all I need to do is just buy, well, I already had the soldering iron, which you can easily get a soldering iron, and a solder sucker, which a pack of these was, I think, $7, and 3 of them came in there. So it's definitely worth it. I have a lot of vacuuming to do, and I have no clue what I'm gonna do. Also, I have a huge amount of keycaps, which I don't know what I'm gonna do with those. Probably give them to my little brother. But other than that, I'm surprised that it went so well. And oh, last thing. This is a DC fan that has a carbon filter on top of it that I cut out, but hooked up to a, what do you call it? A 12 volt DC power supply. And this is my fume extractor, which allowed me to solder inside without having the fear of breathing in God knows what fumes. So, alright. Thank you so much for watching. We'll see you in the next video, and hopefully I'll be able to use these keycaps for a different project. Hello, and welcome to Sealio's Projects. Today, I'm just going to talk about the reason why I personally believe that old hardware is a lot better than emulation. So, the main reason why I love hardware more than emulation, and by hardware I mean using the original hardware like Windows 98 instead of using a Windows 98 emulator, is because I have ran into so many problems where I try to use a software, I try to use an old device, I try to play a video game, and it just doesn't work on an emulator. But it does work on a Windows 98 computer. I have, I think, 3 functioning computers that are able to do Windows 7 and all the way back to Windows 3.1. I think you can go a little bit farther, but I've used them a bunch. I have a laptop that I got from a police thing that currently has Windows 95 installed on it. I have a EdgeTech 3200XS, which has which is running Windows 2000 Professional, and I've used both of them for old cameras, like the Handycam that I have to the side over here. I just photo scanned it. I've used it for drive reading, which is the reason why I have this this floppy disk, and it just didn't work. Like, I couldn't do those same type of things on an emulator, because in my case, unless you have a specifically built emulator, like I mostly use Oracle VMbox. What'll happen is you can buy a drive adapter, but if you're in an MS-DOS style format disk like this one, it will not read the disk, because the thing is, Windows still has to interpret it in a certain way so that the program can still use it. Now, sometimes you can get adapters that act a little bit finicky, but then you're spending enough money that you could just buy a Windows 95 drive. So that's really the main. That's happened to me so many times. I mean, I have an old joystick that my dad used to use when he was in college. It's 2 buttons. It has the letter CH on it. I don't know. It's a white one, and it's still fully functional, and it's analog, and it works perfectly fine with like an Arduino and stuff like that for positioning. But I couldn't use it with the Sound Blaster card with an inside of an emulator. But as soon as I plugged it into a Sound Blaster card, an ISA one, which is pretty cool, it worked perfectly fine. I didn't even have to install drivers, just because it functions analog, which I guess that's the main reason why I personally, another reason why I love hardware. Most old hardware just worked analog style. If you looked at old ISA cards, a solid majority of them are just hand soldered with a bunch of DIP switches, DIP switches. So it's switches that you pop up and down. You might find them in arcade machines, and they're just on there. It functions through analog. Of course there's some digital aspect because it is computing, but it's analog signals. It's not like mice nowadays where where there's stuff inside of the mouse that actually tell you. I'm not describing it very well, but it's a lot more basic, I guess is the best way to say it. And you can't just plug in like a USB drive. Like, you need to tell the computer how it works. Like, you need to have specific drivers for it, and if you don't, then you're screwed. So Windows 95, Windows 98, they all have these drivers that make it possible to use. If emulators sometimes don't have those drivers. Now, you can sometimes use a Windows 95 disk or an IMG file and install Windows 95 on there, which then it will have those driver files. The only thing is, though, you'll have to buy an adapter that's compatible with the emulating software, which that can be a problem, because let's say you buy a cheap random one and it just doesn't work with the software, then you're out of luck. So what do you do then? Nothing. So you're sort of out of loss when you're trying to use old stuff. I mean, thankfully PS2 keyboards like this one that I refurbished, they work perfectly fine. You just have to buy an adapter. But when you get into these older things, like for example, I have a Tektronix 460A oscilloscope, and it requires a super rare, I guess you could call it rare, adapter to connect it to a computer. Now, if you have a modern day computer, I think it's like GPDT or something like that, that's the port that's on the oscilloscope. If I were to get a GPDT to USB adapter, it would cost $3,000. I'm not even joking, because I actually asked my workshop if I could possibly get one, and they said no, which makes sense because I originally thought they were going to be cheaper, and then I looked it up, found that it was $3,000, and then it wasn't even worth me asking them again. So on a Windows computer that I have, my EdgeTech 3200XS, it has an ISA card slot. That ISA card slot, which is one of the original, what do you call it? One of the original expansion card thing, that's the word, expansion card slots. That, I have an adapter, GPDT adapter. So all I needed to do was take two female GPDT adapters, solder them together, just using normal copper wire, and plug them in. And that was it. I didn't have to download any drivers, didn't have to do anything, because thankfully I had the original software, which just so happened to be on these floppy drives. I don't want to take out the oscilloscope because it's currently holding up a bunch of stuff, but it worked perfectly. I saved myself $3,000 by using a computer that I got for free, and I don't know, maybe 30 minutes of soldering. So it's more, I guess, well, to sum it all up, I love them. Emulation, it's usable for certain softwares, but when you get into any hardware, emulation just does not piece up to hardware. Because some people might say, well, this hardware is going to die out. It's not going to work well. Well, the thing is, a lot of CPUs that still exist, like the Pentium 4, Celeron, dual core, and all these things, certain motherboards have the ability to decrease the clock speeds. Like, I can run Windows 95 on a 1.4 gigahertz speed. Meanwhile, it's a Pentium 4 thing. It's a Pentium 4 CPU. So you're able to deprecate and decrease and slow down these CPUs so that you can still use it. And you could just easily go online and buy these CPUs and buy this stuff. And most motherboards also from those times, you can just replace parts on it really easily. So I forgot where I was going with this. But hardware-wise, it's better, it's gonna last longer, and it's just more compatible out of the box. And most likely, you're not gonna have to go around and dig through all these different things to figure it out. And if you say, well, just buy an adapter is great until either A, it dies and doesn't work, or B, you have a disk that you can't read on a modern operating system. Windows 7 was, I think, the first, if my little brother's right, was the first operating system that didn't have DOS on it. Or at least wasn't like a DOS-based system. So the problem with that was, or was it Windows XP or Vista? Regardless, Windows 10, trying to read MS-DOS encoded files on a floppy drive with an adapter just does not work. At least for me it hasn't. And I have 50 to 60 floppy disk drives, or floppy disks. So it just, when you can't access the files using modern day techniques, you have to use the old day techniques. And these computers you can get for free. Like, you go to, you go to a school and say, hey, do you guys have any ancient computers? I bet you good money that someone there's gonna say, yeah, we've had this computer in storage since like 2006. I mean, that's how I got the EdgeTech computer. The year that it was made, the computer was worth like $15,000. Now, I mean, it's still worth a pretty penny because it has specialized hardware on it. I got it for free. And the computer I got from a police thing, there was a crime at my school, blah, blah, blah. They gave it back to police. The police gave it back in evidence, and now it's mine. Fully legal, by the way. They just didn't have anyone to give it to, so they said, hey, you want it? I said, sure. So they're free to get, they're super easy, and they don't cost money. $3,000 for buying an adapter versus just having a computer that has the adapter on it. And if you can spend, like, you just maybe spend half an hour looking for that connector on a computer, you can most definitely find one. Because people like me exist, where they don't retrofit stuff, they have stuff that gets retrofitted. So in other words, you would buy an adapter for the computer, the old computer, so that it can use modern day hardware. Not the other way around, where you have a modern day computer and it uses old hardware. Because going from because having an old computer that uses new hardware is so much easier because people make hardware compatible with that. It's not the other way around, where you have a modern day computer and you're trying to get old hardware to function on it, because certain protocols might not be known yet or might not be fully compatible with the adapters and stuff that you're using. Which, again, that brings up the old, of course, MS-DOS style encoded discs, which I wanted to play Doom, and I actually found my dad's old original Doom games on here, and I just couldn't copy over the files. I wanted to actually look inside the files and see what was in there, but I couldn't do it because they were encoded. So, yeah, and granted, this could all be an error on my part, but the second I put it into my EdgeTech 3200XS, I was able to read it perfectly fine. When I put it into an MS-DOS based operating system, it was perfectly fine. So, I guess that was just a rant that I've been wanting to do for a good while. Yeah, I personally just, that's what my feelings are. Emulation, is it still good? It's really great. But hardware is always better in my opinion, because with hardware, you know it's going to work, and it's the best way to test something and make sure that it's still functional. I mean, I have a bunch of graphics cards. They're AGP. How am I going to test that they work? Am I going to buy an adapter? No. Why? Because the adapter might not work with the graphics card, because it might just be a weird graphics card. I mean, I have certain graphics cards which NVIDIA hasn't released a driver for it since 2005. I think, actually I don't remember which one it is, but what are you supposed to do then? Do you look up online, or do you go and you say, okay, Windows 98 had generic drivers that allowed you to use this card, so that when you go and say, okay, does this card works? Plug it in, you plug it into the wall, yeah, it works. There you go. You can test all of these things with your stuff, so that you know in the future when you go and say, I wonder if this works. Oh yeah, it does work. So, yeah. And my dog, he's back here, he's just chilling, because it's thundering and lightning outside. So, alright, well, I know it was just a rant, but thank you so much for watching, if you're still watching, and I will see you next week. Hello, and welcome to Sealio's Projects. Today we're going to talk about how emulation can be better than hardware. Emulation can be better than hardware in a few ways: mobility, price, and ease of use. Also, access to the materials. To start off, price. Most Windows 95 machines, if you get them made specially by companies, they can range from $5,000 to $10,000. Meanwhile, a software similar to Oracle VirtualBox is free. And most old style Windows programs are on places like the Internet Archive, or you could just download them off the internet. Just be safe when you do so, because there are a lot of places that do include malware and viruses. Now we're going to talk about mobility. Mobility pretty much means where can you use this, and how easy is it to get the hardware from your base to where you're going to be working. Now, for me, Oracle VMware, or VirtualBox, works perfectly anywhere. You can run it on a server, you can run it on a laptop, or you could even remote into your computer, but that's sort of cheating in a way, because you're not actually emulating it where you are. You can also run it on certain phones, which is pretty cool. DOSBox used to have a thing for the iPhone, but I think it's discontinued for a very long time now. So, compared to the original hardware, which with an EdgeTech 3200XS, which could weigh almost 400 pounds, or a laptop that you cannot afford to have destroyed, being able to just pull it up on any laptop, any cheap computer you want, is awesome. Because most computers nowadays, even the super cheap ones, even a Chromebook, should be able to run something like Windows 95 or Windows 2000. I wouldn't say anything more than that, because it could get a little bit too strong, but realistically anything can run it nowadays. I mean, this could probably run two instances at the same time if you're tech savvy enough. Now we're going to talk about access. Stuff like Oracle is free. Oracle VirtualBox is free. It's super easy to find. It's compatible with most platforms, Linux and Windows. I don't know about Mac OS, just because that changes by the day. So it works pretty much on everything. You also can get it for free. You don't, as long as you're not a company using it to make money, you can use it for free. And it's compatible with pretty much anything. So if you want to run an old Windows 95 file, you can do that for free. There's no extra additional costs that you need to pay for. It's not like VNC server, which just recently changed its ability to, or your ability to have 4 computers. Now you can only have 3. Sorry, I'm just a little bit annoyed about that because I had to change a bunch of stuff. And that, in comparison to older hardware, which just the availability and accessibility by price, you might be spending $5,000 on a computer, which I know this is harkening back to the price, but it's the availability of these items that harsh the price. So you could go on eBay and buy these parts. They do exist. It's just they could range from $20 to $500, which again, it's harkening back to the price, but it is true. So, when it comes to availability, what I've found is best for these types of, when you're trying to run older softwares like Windows 98, Windows 95, Windows 2000, all these old things, the Internet Archive is the best place you can go to grab these things, these image files. And the best part also with these programs such as VirtualBox is that you can use adapters with the computer. So in other words, if you need to read a floppy disk in MS-DOS format, sometimes, and the keyword I say sometimes, you can buy an adapter, floppy disk adapter, plug it into your computer, and then connect it and have the Windows 95 computer interpret that drive as just a normal connected floppy drive. This has had very mixed results for myself. It depends on Windows if they support it or not. It's very, 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 very finicky. There was a video game that I used to play using a virtual machine, and it stopped working because Windows decided to update it and not allow you to have any more MS-DOS files. Well, at least it couldn't work with MS-DOS files anymore. It was a little bit finicky, because the thing is, which is one of the tiny problems that I have with emulators, is that the program itself has to interpret the data. The thing is, Windows has to interpret the data before it gets to the program in the first place. So if it can't interpret that data, it's not going to work, and you'll get drive failures, and it sucks when you spend a lot of money on an adapter just for it to not work. So yeah, I mean, that's really all the qualms I have with emulators. I mean, they're not horrible, but my heart still has a place for hardware, because realistically with hardware, everything's gonna work and be great if it's something that's baked into the program and hardware. But with the emulation, you can download files and get them much easier onto your computer. You also can connect these old Windows 95 images to the internet just by using the program. So in other words, if you want to see if you can play a video game or search something up on a Windows 95 file, you can easily do that, which I have done before to see if you can actually emulate stuff, or if it was to see if you can actually connect to the internet, or if my card was broken. It turned out that my card was broken because I was able to clone the drive, turn it into a disk image file, take the disk image file, turn it back in, well, take it and turn it into a VirtualBox file, and then from there I was able to test it, and it was able to connect to the internet, and there was no problem. So, I guess that brings up another point. Emulators, they're great for testing. You also don't risk blowing up any hardware, which thankfully, knock on wood, I have not destroyed any hardware yet through emulation. And yeah, just hardware, in my opinion, it's better, but emulation definitely does have its place, just because it's free, it's easy to use, and there's minimal risks. I mean, as long as you don't go to a weird website, download a Windows 95 file, and then Norton pops up and says, "This is a Trojan file. We did not allow you to keep it." So just make sure when you do download those image files, make sure they're safe, and make sure that they're also legal. Don't go pirating, because certain websites, they're really not safe. So you'll be able to find stuff for free, but just make sure they're safe. So I guess that's really it for this weekend. I cannot stress how much I love Oracle VirtualBox. It's great, especially with adapters. As long as you can buy a PCI to PCIe adapter and stuff like that, you can use most expansion cards, which means most old video cards, which is pretty cool. But yeah, thank you so much for watching, if you're still watching, and I will see you next Sunday. Bye. Hello and welcome to Sealio's Projects. Today we're going to go over how I went from V1 to V6 for my electric skateboard battery holder. Like all good projects, it all begins with a single sketch. This paper contains all of the sketches for each of the battery holders. This even includes the base models. So the only problem with all of this is that we were off by ½ centimeter, and the ½ centimeter was found on V1. V1 was a hole test to make sure that the holes matched up with the board, which I will show later. As you can see, it broke off a little bit, but as you can see written on here, battery holder V1, test. Cable holes, I need to move them 0.85 of a centimeter. And the back holes, I need to move forward ½ centimeter, either forward or backwards. Regardless, I had to move them. This was February 24th of 2023. So this was just a perfect test. And it also printed straight up and down, which is pretty awesome. So now, we get to the second version, V2. V2 was the first model, as you can see with how grody and dirty it is and how duct tape it is, to see actual service. Now the problem with V2 was that it wasn't rounded, and when you have just sharp corners and thin, well, not necessarily thin, but just sharp corners and thin walls, and it hits the corner, it literally falls apart. As you can see here, the thing literally just came off. I remember I was standing on the board, accidentally sent it into a door, and I don't know if it was the wheels that hit it or just the impact of the door, the thing broke. And the door was literally just held on by duct tape, which that's an important thing for later. So after a huge amount of holding it back together with all of this different, just melting 3D printer plastic and just putting it on there, you got some Mars up here, I decided that we needed a whole new version. This was also cut off of the door. Originally it was supposed to be about here-ish, which the problem with that was it just was extra filament and was blocking putting in the batteries, which ended up being just useless because I would have to take off the tape every single time and it would scratch up the batteries. So needing a new design, because this was effectively just not safe and not the greatest, we then ended up going to V3. V3 doesn't look like much, and you can't probably tell why. It's very, well, it's only half. If you look right here, which I'll see if I can zoom in, there's a massive layer shift in the print. So that massive layer shift was a problem, because as you can see, this isn't the print being finished. This is how thick I was printing them to make sure that they were strong. I mean, you can't really break it. So the problem is, if I printed this entire thing in one piece, what would happen would be, if there was any layer shift or any movement because it was in my college dorm, the entire print would be ruined, because this offsets the holes by enough where it actually causes a problem. So then I thought, okay, how do we get around that? We print it in two parts. So V3, but in two parts, is V4. V4 was by far the most successful iteration at the time. It originally had, actually, you know what, I'll peel it off here. It originally had old bandsaw blades that I had cut up and fused into the middle to hold it in. It was going great and was functioning perfectly. As you can see, it was split down the middle, and it was held together by crazy glue, until I hit a bump and the thing just bottomed out. It split from under, and yeah, when you're traveling with lipos and you don't want them to explode, it's not really helpful. So, well, first, before I get to what I did to fix it, as you can see, the corners are rounded to help with deflecting angles, and the door is held on by screws, which means it's super easy and I don't need any more duct tape, which meant that this is a perfectly renewable and redoable process, which made my life a huge amount easier. This saw use from for pretty much the entire school year once I had gotten the thing. So it was February to about May, June. So this served me a good 4 to 5 months, and eventually did fall apart. I did try fusing it again. It didn't really work. Thankfully, the screws that were holding this into the board were acting also as structure, but this needed a fix because I couldn't ride around having the fear that if I hit a bump hard enough and the screws were out, it would just open up and I would be riding on a ball of fire. And so now we get to the still in use V5, the crowning achievement of this entire project. Now, V5 had a tiny problem. I originally was using the school-given SolidWorks, which was 2023. I have an OEM offline installer version of SolidWorks 2021 Premium. And if you've ever used SolidWorks before, you know that you can go forward, but you can't go backwards. So the files that I used for V1 through V4 were useless. I couldn't do it. So this is a derivative of those files in the way where I took the dimensions and I recreated it faithfully. Now, there are some differences, but overall, it's essentially the same. It's nearly a 1-to-1 ratio. So the holes are still the same for the screws. That's just filled with glue, just because I didn't want to lose the bolts, which kept happening. Because, I mean, bumps are going to loosen the screws. So that is, yeah. I also cut it long ways in half because then it would be much harder and the batteries would put weight on both sides instead of just on the middle. So it'd be a lot harder to break. I also decided to go a little bit crazy. This white stuff that you see is not dirt. That's JB Weld. That is effectively crazy glue, but industrial size, or industrial type. So this was able to keep it from breaking. I mean, this thing is a brick. I stood on it and it didn't break, which was absolutely awesome. This thing has hit the ground so many times. It's been scratched up, it's been destroyed. This has essentially served me for, what, 2 full semesters, so almost an entire year. It's absolutely amazing. I made this in June-ish, I think, of last year because I needed something to replace V4, and this was done. I literally had the Prusa sitting right there, printing in a cardboard box, and it worked perfectly. Now, the other thing with this was originally, I attempted to do a fully toolless battery removal, and right here, as you can see, there is a little hole, or there's a, what do you call it, a circular cutout. That cutout is for, what do you call it? That cutout is for a magnet. It's supposed to be a neodymium magnet, or neodymium, however you say it. And that would also connect onto a door. This is not the original door, this is a secondary door that I made, which once you would slide it in, the magnets would hold each other together, which it worked really well until the same exact spot that killed V4 took the the door and bounced it up and down a little bit and flung it out, which thankfully I heard it happening because I heard the magnet fall off and I stopped immediately. So I ended up saying, you know what, oh well, and I went to using a screw on the door. But it's a single screw plus a lip. This just slides right in there. Sometimes you gotta lift it up a little bit and it goes perfectly in there. And it's absolutely perfect. I mean, I have had 0 problems with this at all. Because the thing is, it's encapsulated on both the top and the bottom. So it's really strong. I would honestly trust this with my life. That's how awesome this thing is. And so now, the batteries that we were using was a 9,000 milliamp hour LiPo 4S and a 5,000 milliamp hour 6S battery. The only problem with that is, as you can probably guess, when you use one battery that drains too fast, you almost kill it, which I did kill one. Thankfully, it killed it to the point where I just drained it a little bit too low, so it couldn't be recharged. So, not the end of the world, but still not the greatest. So, in fear of this, I wanted to see if I could make myself a better battery, a battery that would be perfect. Now, I didn't want to use V5 because V5 was for lipos. V5 wasn't really, like, I had to remove the batteries to charge them. I did not want to do that with this new battery. This was going to use lithium ion cells, specifically 1850s I had pulled out of my scooter. And that leads to V6. V6, the final iteration, up till now, of the skateboard battery holders. Now V6 has a bunch of holes, and it's literally V5 with no sliding door, holes on the side for the different mounting places, and that's really it. It's V5, but with less and more holes at the same time. So this did see some use, and then I ate it twice while riding, because the problem with the lithium ion cells that I was using was that since the bike ESC, since the skateboard ESC uses, uses regen braking, it puts power back into the batteries, and the ESC didn't like that, so with the lithium ion cells, and yeah, it would essentially just lock up and stop, or it would just break and do whatever. It wasn't good, and I ate it twice and fell twice. Thankfully, it wasn't this that caused it, but it was something else. So, yeah, so I ended up having to scrap that project, and I just stuck with lipos, which has led to a different skateboard being made, which you'll see in a later video. And yeah, but I mean, overall, V6 could literally be used as V5. Like, I could swap it out if I wanted to, and I didn't want to use the door, and I just wanted something to be more, just to be safer. It has JB Weld, but it also has hot glue, so it's a mixture. The JB Weld was the thing that holds it together. The hot glue was the thing that keeps it from going in the water. But, I mean, it's got holes that go all the way through, so I would have needed to use a heck of a lot more glue. The way how it would have worked was the BMS would have sat right here. And originally I discharged from the BMS, then I switched to discharging not from the BMS. Both just were terrible options. And we'd have one cell pack here, one cell back here. It was a 10S2P, so it gave me about a 5,000 milliamp hour battery, which was about the same, and it was pretty good. Like, I could have easily just plugged in the charger right here, and it was perfectly good. It just sucks that it didn't work, because, I mean, it would have been literally perfect. So, yeah, but I mean, that's V1, V6. This was literally, and I do mean literally, the first project that I ever did extensive designing and prototyping for. So I'm happy to share this with the world, and it just shows that 3D printing really is great for rapid prototyping, and sometimes even a final product, because once you get it right, you're pretty much good. Like, I could get this injection molded if I really wanted to. Will I? No, because the 3D printed one's perfectly fine. I could replace it instantly. So, I mean, if you end up designing something, just design it. You can use Tinkercad, you can use Onshape, you can use a whole bunch of these free softwares. But once you have your design, just only change small parts of it. Unless you really need to change a huge amount, like going from V4 or V2 to V4, you can change a lot, but just make sure you keep the stuff that works. Because if you change everything, then you're just creating a whole new design. Yeah, I only changed the parts that broke and weren't good and weren't, well, quality of life problems. So by doing that, I made something that's indestructible, easy to remove the batteries, easy to replace, and takes the least time for printing. So you can do whatever you want, just that's what I suggest. Make the changes short and sweet, unless it's something that really, really, really needs to be done. And cutting up your parts, always make sure that you do a cross section. Don't just do a flat line, because it's a lot easier to shear something on a flat line than if it's intertwined like that. So, yeah, I'm happy I got to share this with the world. So, thank you so much for watching. If you're still watching, I will see you next Sunday, and I hope you have a great day. Hello and welcome to Sealio's Projects. Today we're going to see if I can revive my dad's dead flashlight. So, to start off, this flashlight just doesn't work. And when you plug it in to the wall using an adapter, the light on the actual adapter shuts off fully. So that is with it plugged in, that's with it unplugged. What it should do is it should go to a red LED. So we know that something inside of there is bad. So we're gonna see if we can still bring it back to life. So the first thing we're gonna wanna do is take this thing apart without destroying it, which we should be able to do because I'm assuming there's screw holes under here and I don't really see anything else besides maybe the lens here. So let's get it started. Open the Strabito set. Alright, so we got all 4 screws out. So that just pops straight out. It looks like there's just some styrofoam and what looks to be a 4S1, no, a 1S4P lithium ion stack. You can see the 4 cells and the wire, which makes this very easy to deal with actually. So there's literally nothing else inside there. It's literally just charging module, batteries, LEDs. I mean, I thought there'd be something more, but no, that's really it. That means I honestly, I could probably in a later video take this and quadruple the capacity by using some 21700s that I have left over. But to see if it's dead, since all these cell packs, since the cell voltage should be the same, if this is under 3.2-ish volts, that could be the reason why. So we're gonna see if it's dead because of the batteries. Interesting. The batteries are at 4 volts, which means that, yeah, they're at 4 volts, which means that this should work. So then why isn't it? Let's see. We're gonna use a flashlight to see inside if we can see any burning. No? Ooh, actually, no, I don't see any burning. Why isn't this working? I mean, you get absolutely nothing when you press the buttons. This looks like it slides off. So, and this is connected. Yeah, so all the batteries are connected, so that doesn't make any sense. Why it's not just working. So that means that there actually is something genuinely wrong with it. Okay, let's do this. Okay, so we have the main LED, which looks like it goes up to their screws. I mean, the LED doesn't look burnt out. There is some little amount of film left on the back of this, but it doesn't look like enough film to kill the thing. I might go grab some wires to test the LED. So we know the battery's good. We know the LED's good. I'm assuming these on the bottom are good. This is interesting. Is there a way to take this apart? No. Alright. I'm gonna go grab a soldering iron to desolder this stuff so we can start doing stuff a lot safer. Alright, so of course, safety first. The first thing we're going to do is we're going to disconnect the battery from the circuit just so I can fiddle around with anything and make sure I'm not going to start a fire. So, always disconnect the positive first, because the positive is what carries the voltage forward. So now it's just a cell back. So, with that done, we're now going to also take off the LEDs, which it is marked, so we are good for that. I think it is a battery problem. I think it's actually a button problem, not a battery problem. Alright, so we have that desoldered. And let's not desolder those just because I don't know where those go yet. Alright, so we got that stuff desoldered, safe. Because this, since it's literally just a button to turn it on and off, we can utilize that for other stuff. Like I might be able to throw it on my skateboard. So, keep those on. Ideally, it would be great to harvest this stuff just because these LEDs are very bright, and the fact that it uses a single cell means that you can easily put together a very, very, very large battery. And it also has a power bank attached to it, so it's a free power bank if I save it. Okay, so we just took that out. It looks like I'm gonna have to pop off this top to get to where the buttons are, which I think is the main problem. So that's just something that you shouldn't do. Use a Phillips head screwdriver as a prying tool. Almost got it. I assume this is either glued on or it's supposed to pop off in a special way. I mean, it does slide out right here, but it doesn't want to slide out, so yeah, I think we might have to go with thinner. I think it's glued on. Alright, we got it open, now we just gotta crack the shell. Alright, so that took a lot longer than I'd like to admit, but we finally got the button panel out, and apparently it is a lot more than just LEDs and a button. There's an entire circuit on the back, which, by the look of it, is perfectly fine, which raises even more questions. So, let's dive even deeper. Okay, so we finally have the module, the control module, which, looking at it, I don't see anything except maybe one transistor that died? Can't really tell. It's in the middle. It's the only one with a little bit of a weird coating on it. I guess one thing that I can definitely try, well, this we know is a charging module. So we've already won. We've already picked up a charging module. This, we might be able just to power straight off of that. It'll be a little bit sketchy, but it should work. So I'm going to go grab some wires. Alright, we have our testing wires. Thankfully we know what's positive and what's negative. Alright, we have our two wires soldered. This is the positive. This is the negative. And we're going to see if we have life. Ooh. Okay, so we have life, it works. Now, I have absolutely zero clue how to control these. Now, I don't know if this had a different diodes inside of each of these diodes, like different colors inside of each of these diodes. I probably should have soldered it to the battery pack. Alright, so now we have the wires soldered to the battery pack itself. We're going to see if we can power this LED strip with just this. So it looks like they all have common ground. So they all have common power, different grounds. So, I mean, the power. So, I mean, let's see. See what happens. So, that looks like it goes to. Okay. That just. it connected for a split second, and this wire got exceptionally hot. Whoa. Well, my retinas are burned, and I almost just burned my hand. Ain't that great? Wow, it's bright. You know what? Okay, for safety, and so I don't do that again when I get my eyes burned, we're just gonna. Yeah. Okay, so we now have it soldered directly to it. So L1 gave us the bright lights. Let's see what L2 does. Blue, red. Oh, what? Okay, so L1 is white light. Ah, it's so bright. L2 is blue light. L3 is red light. Okay, and it just plugs in and works. So that's really it. Okay, so let's desolder this. Let's get it off of there. Okay, so the parts that we have left, that we know work 100% are the main LED, the LED strip. We don't know about the charging module, but I can test that really quick, just by plugging it into the battery as per normal. And I can go and grab a portable charger that I have to see if it charges. So, alright, so we have the battery soldered. We are plugging in the USB, and hopefully this will charge, because that means that the charging module is good. Interesting. Just making sure it's the charger before I get rid of it. I'm just gonna make sure now it's not the cord itself. So it's not the cord. So I think that this died because my dad, like the flashlight we have over there, likes to leave stuff charged in constantly, and when you do that, the charging module on here gets overloaded, and it can only be hot for a certain amount of time before it fries itself. And that makes sense why the battery was still good, because it was charged up, but it was at 4 volts, not 4.25, which would normally be. So I think that this might be perfectly good. No clue what this even does, if I'm being honest, just because it makes no sense. Now I know what this does. So what this module does is that once the button is pressed, it's going to maintain a constant source of power to the lights. It's not like a switch. Well, no, it acts like a switch, but it's a button. That makes a lot more sense, which will also explain why this thing was fried. Because one of the buttons was to turn on the lights, or one of these, the two of these on the sides help turn on the lights, and the one on the middle, that one is probably what's keeping that continuous charging through. So that's why it fried, because it was on for way too long. Yeah. Alright, but, I mean, we couldn't save his camera, the case in point, but we can definitely get our money's worth out of this. So, I think in the next video that I do, we're going to take this, and honestly, maybe even this, because this is really easy to work with, and slap it together into a new flashlight. And honestly, I might even ditch this battery pack just so I can have a much better one. And I also do have some 5-volt charging modules, so I should be able to utilize, utilize this stuff. So, there you go. I mean, that's it. So, we now know. It was, maybe I should just solder that actually. To me, that's constantly open. Good. Alright, now we can get back. So, the only problem that this thing had was this charging module, which makes sense because it was left in for so long and just plugged into the wall. I mean, this was probably plugged into the wall for a year or two just straight, which probably is the reason why this thing died. I mean, it's not super high quality. I think it was like $10, $15, but the LED on this thing is pretty crazy, and the LED strip on this can do multiple colors and different stuff. So honestly, with a bunch of switches, which I do have, I can easily wire this thing up to work really well. And with a 3D printer, it should be perfectly fine, because if this thing overheats, it's gonna melt the plastic and not my hand, which I like that a lot more. So yeah, I think the next video is going to be me turning this flashlight into a zombie flashlight with 3D printed parts and a much larger battery pack. If I can't, I might just end up using this, but yeah. So thank you so much for watching. It sucks that we couldn't bring it back to life, but we're gonna turn it into a zombie next Sunday. Hope to see you there. Bye. Hello, welcome to Sealio's Projects. Today I'm going to tell you how the charging circuit on this is super dangerous. To start off, this battery is a single nickel something battery. I don't know, the markings have worn off and it's practically exploded. So the way how this type of airplane works, you've probably seen one of them, you take it, you put in the batteries, you pop it in to the bottom, and then you turn it off, you wait a few seconds for it to charge. It literally says in the manual, wait for the battery to get warm. Now, whenever you have a battery that gets warm, how good do you think that is? It isn't. So then, after you wait about 10-15 seconds or the battery to get warm, sometimes you can't even feel the battery. This one is like 10-15 years old, so I can't really tell, and also it doesn't really hold any charge. So then you unplug it, then you just take it, and it goes. So now you might be asking, well, so what's so dangerous about it? And I just broke the tail. Well, the reason why it's dangerous is because the circuit inside of that is literally just nothing. You just take the batteries and it dumps voltage into the battery in the bottom of the plane. Like that green thing right there, it's covered up so when it hits the ground it doesn't explode. So once you have it plugged in, like once you have these plugged in, they just create a fully connected series circuit that just dumps voltage into that battery. That's it. Maybe there might have been a resistor or two that I missed, but it literally just dumps it in there because there's no current control. There's a, a constant connection loop. So in other words, when I test it with my voltmeter, it literally just says that there's no resistance, nothing behind it, and it says it's a perfectly good connection to it. And yeah, so it's wildly unsafe for a few reasons. One, if you leave it plugged in for too long and the thing gets too hot, it could explode, it could melt, it could do a bunch of stuff. And well, with batteries like that, they could even catch fire. So it's unsafe. Nowadays, we have things like this. Well, at least what's inside of here. Inside of here, or this is a 10S BMS battery, and it's a 36 volt, 2 amp hours. So that means that there's 10 cells in here, and each cell has 2 amp hours of capacity. So this cord is not connected directly to the cells. It's connected to a BMS, or battery management system. Sometimes it's also a balance management system. It's weird. It's technically both. You could use both words because they both are technically true. So what this does is very important. It limits the charge when you're charging these cells, and also limits the discharge of the cells, which means that once the cells in here get low enough in voltage, so usually when you have them charged at 4.25 volts, when they finish discharging, they're usually at 3.6 volts. And the reason why you want that is because if the cells discharge too low, you can't charge them back again. The chemistry on the inside of them are made specifically so that once they reach a voltage somewhere below 3-ish volts, they literally will disconnect, and you're not allowed and you can't charge them because it makes the chemicals inside very unstable and very well, yeah, just unstable. So having something like this that controls how much you're charging it by and how much you're discharging it by is really useful. And they didn't really have that back then, so stuff like this, it was just, if it feels hot, unplug it, wait a little bit, and then throw it. So, yeah, it's really unsafe. So, because if you leave it plugged in, you'll burn your hands, and there's a reason why they don't have these anymore. Apparently, something happened with a kid and burned a finger. It might have been me. But, what do you call it? So, that's really just so unsafe, where you have no BMS versus BMS. Everything you buy has a BMS, except the lead battery. Only because those lead batteries, it's really hard to get them to go wrong. Like, it's like if you've ever taken a lead battery, you could drain so much current from it, it's crazy. I mean, granted, the voltage will drop faster, but you're not gonna get a huge explosion because it's lead. Now, if you do that with a LiPo battery, or a lithium-ion battery, anything with lithium in it, and you drain it really quick and too much, it's gonna heat up, catch fire, explode, and you're gonna have a nice bill for repairs on your hands. So another thing that they could also technically use is something like this. And here, let me unplug that. This is a balance charger. You take lithium polymer batteries or lead batteries or whatever you want, you plug it into here, and this charges it at a slow rate and safe rate, constantly monitoring the voltage to make sure that it actually charges. So if I were to take something like that battery and charge it with this to make sure that the voltage doesn't go too much and I'm not charging it as fast, it'll be a lot safer to use. Instead of this, which is just dump current into it, dump voltage into it, have fun. So this type of stuff is really, really useful. Granted, these are a bit expensive, but they're worth it, and, well, they overheat sometimes, so you can see the little DIY hack that I did, plus a Dell power supply, because this thing works off of 12 volts. So, yeah, that's really it. Just the fact that it's, try and get it right, versus the computer will tell it for you, or the computer will tell you to unplug it, is, yeah, it's so much less safe than modern day stuff, and that's the reason why everything you buy either has a BMS in the cable, or the charging management system in the cable, or attached to the battery itself. So if you ever find one of these, just be careful. It's not as smart as you think they are. That's the reason why these were made for so cheap. And yeah, let's see if this flies without a tail. Nope, and it fell apart. So we'll see you next Sunday, 8 a.m. as per usual. And yeah, it's gonna be the zombie flashlight one. I just wanted to say that the reason why I'm doing this video instead of the zombie flashlight is because the zombie flashlight is taking a while to edit. The video ended up being over an hour long when I was filming it, not including the extra stuff that I had to add in the middle. So yeah, cutting down a 77 gigabyte one take is not very fun, but I'm gonna make the video anyway. So I will see you guys next Sunday. So this should be the red one. Good, this should be the main one. This should be the blue one. Okay, and this should be the white one. Hello, welcome to Sealio's Projects. Today we're going to be creating a flashlight from these broken flashlight parts. So if you haven't watched the video that came out before this, these flashlight parts are from my dad's flashlight, which died. We tried to save it, but we found out that the charging module was bricked and we couldn't use that anymore. So I decided to take it apart, reprint a new backplate, and we're gonna see if we can create a whole new flashlight out of it. So we're gonna be doing a bunch of stuff: soldering, gluing, drilling, and I just wanna start off first with popping in the switches. So the LEDs are going to use switches instead of buttons, just because switches, they're much easier to work with. So we have 4 switches, one for the red LED, one for the main LED, one for the blue LED, and one for the white LED. Alright, so those are all 4 popped in. I designed this myself, which I'm pretty proud about. And we have that. So now we need to drill in this. This is the charging module, which connects into, or at least is a charging port, which connects into this, which will charge the cell. This is 4.2 volts, which just means that I plug that straight into this and it will just charge it up and not overcharge it, which is perfect because that means I don't need a separate charging module. It's a dumb way of doing it, but it still does work. So, I'm just gonna plop it in there. There's a little standoff, as you could probably see, and what we're gonna do is we're gonna take it, we're gonna drill, hopefully not through. Okay, now we're gonna take one of our screws, go through. Actually, I need to go get a different bit. This is too big. Alright, so we just got a thinner bit. Now we're gonna screw it in. We're gonna screw one screw in, and then we're going to screw in the other screw, just because I did not want to have to design more screw holes on this thing. So, we have the back plate assembled, as you can see. Nice 4 switches and a charging port, which you can push really hard into, but since there's screws, it's not moving. And we're now going to solder this harvested 1S BMS that I got off a really cheap, I forgot what it's called, but a really cheap battery. And we're gonna just take that and solder it right onto here. Hopefully, since this is a low power application, should work. So, I mean, here's hoping. Worst comes to worst, we just buy a 1S BMS, but if this is worth a try. We're just harvesting stuff from broken stuff. We're not buying new stuff. So, alright, I'm gonna wait for this to heat up, and once it heats up, we'll continue. Now that the soldering iron has heated up, we're going to take the battery and we're gonna solder the BMS to it. Thankfully, it has it, even though it's so cheap, it has it actually marked, which is positive and negative. So, oh, and pro tip, if you have wire and you don't have a place to like put it on the spool, just take a hole, or just take a drill or a soldering iron and just put a little hole through it, so that all you need to do when you're done with the wire is just feed it right through, and there you go. The wire will not become undone. So this is just going to pretty much just sit right next to or right on the BMS, but since we have a lot of space, we're going to just pop it off. I actually need to grab some wire strippers. Alright, so we got our wire strippers, so strip a little bit off there. Strip a little bit off there. Take some solder and tin the wire. Ooh, wow, I just flung a bunch of solder around. Okay, also make sure you wear glasses when you solder, because sometimes the rosin core can splatter if you're doing a lot of soldering. So, be safe. Ow. I have no clue what that was. So that is the positive. I want to solder to the negative. Alright. So we have that. And I think I want to do the final connection, which is going to be between the positive and the positive and the BMS. I think I'm going to solder the positive onto the BMS first and then onto there, which technically shouldn't make a huge difference. I plan to discharge through the BMS, by the way. Alright, so that's our first thing done. Now we just need positive. Alright, so we have the BMS soldered to the cell. I'm going to go grab my voltmeter because that's another thing I forgot, and just make sure that this is outputting a correct voltage. So we got our voltmeter. Let's make sure that we soldered correctly. Good. So this is reading at about 4 volts. So this BMS should be reading at about 4 volts. Don't want to short anything. 4 volts. We have a success. So now that we know that the BMS works, I think the first thing we're actually going to do is cover it in glue. Just because the fact that this BMS is very exposed on pretty much every side, and this is a metal casing, so if I don't put glue on it, it's going to short, and last thing you want is a lithium-ion battery shorting. in the meantime, while we're waiting, let's just make sure that this thing can actually power an LED of this size. So we're just gonna temporarily solder the negative right here. All right, so if we're lucky, this should be perfectly fine. The cells are definitely rated for this because they literally came from this camera. So let's see. Okay. All right, so the BMS is not warm, and as you can definitely see, the lights were powered. So, okay, I'm actually very happy about that because I had no clue if this was gonna work or if I was gonna have to buy one. So now let's just safely disconnect this. All right, so while we wait for the glue to heat up, I guess we can just go and talk about how I ended up making this backplate, because this backplate was the only part that really was broken because it was using the broken charging port. So I pretty much traced out the outside using the actual original backplate, and then I used some calipers to go and measure a bunch of measurements, and well, I designed it. Then I made it in SolidWorks, which I'll show that right now. And yeah, it's really easy once you have calipers. With calipers, you can measure everything, and then you know just, oh yeah, give it a little bit because the plastic is going to shrink. So SolidWorks and 3D printing has just been so amazing for me to use, and I'm so happy I got to learn it for the last few years. So, all right, looks like we're making some drops. So let's put some glue on this thing. We have the glue on the BMS. It's a lot of glue, but it's a very important part of the thing. So, now we're going to take it and solder the BMS to here. Now, the way how we're going to do that without doing any cutting, is we're going to look at the polarity on this charger. So, as you can see, or I might have to take another photo of this, right there, it says polarity that the outside is negative and that the inside is positive. And since we can look directly at the ports, we know that since the inside is positive, I need to solder the positive to this pin right here. So we're gonna tin the wires, get this going. We now have it soldered, so we're gonna test it and make sure that it is all good, and then we're gonna slap some more glue on it. Why? Because glue is better, because glue is an insulator. So, I'm gonna take the thing and charge it. Now, from the last video, what happened is when we plugged it into the charger, it just straight up went dark. The light on this charger went dark. So, please work. Success! We have red. And there's no smoke, which that's always great. Don't feel any heat. We're all good. Success! So, we know that we can charge the module. Good. So we have the charging portion of this thing finished. So, let's do a celebratory glue. So now that we have the power and the charging part done, we now have to move on to the switches and the soldering the actual LEDs. So for this, since there's multiple different sides, we're actually going to be using a positive control method, which means that this is going to intercept the positive side of the control of the circuit, and from there we should be fine. Now this is going to be a little bit harder to get it exactly right. I mean, I'm just going to use a bunch of wire because I can just throw it around in here, and other than that we should be fine. So it looks like that has dried. So I think I want to start with the big main one, this one first. So we're going to take some nice long strips of wire. That should be more than enough. It's better to do too much wire and then just cut it down when you're done than to do too little wire and then be screwed. So one tiny problem that I do realize, or one thing that we do plan to do, is solder a bunch of connections to this side of the battery. So I'm going to put some solder in the places. I'm gonna need 1, 2, 3, 4. So I'm gonna need 4, so let's add some more. Now, when you're soldering directly to the, what do you call it, the nickel strips, make sure not to keep the soldering iron on there for too long because it will heat up the batteries. So, I just realized that I have a better idea to get this done. So I'm gonna have one positive wire, since these are gonna be controlling the positives. I'm gonna have the one positive wire come off of here, and it's going to connect to all of these in parallel, and then the individual wires will have their own wires that go to the LEDs after. So in other words, instead of having to solder 4 wires to this thing, I only solder 1 wire and just solder 4 connections to here, which is much easier and a lot neater. So we're gonna get that done. Alright, so what we're gonna do is pretty much just take this wire and run through these 4 terminals, because since they're both positive and these are omnidirectional, I can pretty much just have one wire that goes through all of these, and then these 4 wires can go to their individual LEDs. And that'll make it a lot easier in general just for me to do the wiring, because I mean, I'm wiring them in parallel anyway. Might as well just make it easier for the soldering. So I'm effectively doing a wire bus bar, pretty much. Alright, so as you can see, we have the wire that goes all around here. Now we're just gonna just drop some solder and that's it. Alright, so we have all of those soldered. And now I just need a bunch of reds. So let's keep going. Alright, now we're gonna just start soldering to, we're gonna start soldering first actually to the LED, just because it's gonna be a lot easier to do so. Alright, I just realized that I was originally right. It's ground controlled, not positive controlled. So pretty much I can use the same thing. It's just gonna be a little weirder. So the red's gonna be the black. Okay, the red's gonna be the ground. So, okay. It's not ideal, but that's how I've soldered it. Alright, so we got the wire soldered on. It's weird that the colors don't match the polarity, but it's what we gotta do. Since we have a positive and negative wired up, we're going to now just mark which one goes where. So this one could be blue, white, or red. Oh, no. So this one could be any of them. Alright, so that one is blue, so not that one. Very bright. That's red. Alright, so that leaves us with this one. This one is white, which means it needs to be soldered right there. It folds in like that. Perfect. Alright, now actually I just realized before I start soldering any of those, because that's going to be pretty much the last step we do, I want to actually solder the stuff to here, because if I don't, when I close it up I won't be able to solder anything new. I just realized I messed up. The reason why I have a BMS in the first place was so I could discharge from it and charge from it. So I'm going to have to do a little bit more soldering, because I don't want to be discharging through that. Or no, I don't want to be discharging right through the battery, because I'll drain it all. So I just need to do a little bit of unsoldering, so here we go. Alright, so we have partially fixed our problem. Now we're actually getting back to soldering the LEDs. Alright, so we have the LED resoldered, and we have the screws put in. So now all we need to do is just wire these, solder these wires onto their respective parts. So we know that these two lanky boys, remember, so red goes with red. So that will go right here. Alright, so if we have been successful, and once I flip the switch, the light should turn on. Let's go. Alright. So we got that done. Now we gotta get the rest. Which, I'm regretting cutting them so short. I mean, they technically weren't short at the time. So that's off. We want... Alright, so we're gonna try and find the red LED. So that's white. Nope. Blue. Nope. Of course, it's always the last one you try. Red. So this one goes right there. So let's get that soldered. Actually, let's get these all tinned. So putting it in the correct orientation. This. Again, this should be the red one, but it's always good to test before you solder. So we want red. That's why we make sure. I would have soldered that incorrectly. Blue. Red. So that is the red LED. So that's just... Okay, you know what? Let's turn it off. Because we know that it's the right one. For some reason, the solder isn't sticking to it, so I'm going to tin the actual plate. That should make a good difference. Yep. Let's see. Alright, we have the red done. So, this one, let's see. This one should be white. Alright, good. So this one is white. So let's get that done. Alright, that's white, which should leave this one, this last one, to be blue. Alright, so we now have everything soldered. Finally. It's discharging through the BMS, which means that we're not going to kill the cell. So let's see. When I do this, so this should be the red one. Good, this should be the main one. This should be the blue one. Okay, and this should be the white one. There we go. Alright, so now I'm going to throw a safe helping of glue on here. Screw it in. And then we're done. Actually, wait. I'm going to go grab some styrofoam that came with it so that this thing doesn't move around. So. Alright, let's go grab some styrofoam while this cools. Alright, so we're going to take the battery, shove it in there, put this thing so it doesn't move around. You know what? I'm going to go grab more glue only because I'm afraid of the top contacts touching. Okay, we have more glue. A lot more glue. Because I'm very afraid there's two contacts right there on the charging port, which I'm very afraid will touch the ends. So, actually, you might as well clip them first. Oh yeah, they'll definitely touch. What the hell was that? Okay. Guess I gotta resolder it. Actually, you know what? It's good that I need to resolder because I can resolder on the other side and be safe from it touching. So, all right, let's just check to make sure everything works. Good. We're all good. So, just a teeny bit more glue. Get in there. There you go. All right, we got it on there. So, we're going to now screw these in. Actually, you know what? We're gonna do something. All right. So, it's on, finally. And now we're just gonna screw in the last set of screws. Then we're gonna pop on the handle, and there we go. You can also tell because it's got a duct tape everywhere because I had to break it off in the last video. So we finally finished the zombie flashlight. Looks a lot different from the original video. I mean, the handle's different and the back's different. I mean, that's really it. But we now have all the LEDs, each controllable by a switch on the back. We have a functioning charging port, and yeah, so let's just do a quick demo. That's the white light. This should be the red light. This is the blue light. This is the white light. Now, let's see what happens if I do red and blue. I can do red, blue, and white. Unlike the other one, which can only do one at a time. Wow, that's very bright. So, we finally finished it. It only took an hour and 15 minutes. It's pretty awesome. I mean, we have blue, white, red, main, and we can even do blue, white, and red all at the same time, which we couldn't previously do. So yeah, we also have a nice new ergonomic duct tape handle. This is nowhere near waterproof, but I don't think the other one was to start off. We have a functioning charging port, and overall we have a functioning flashlight. So I'm going to show you some videos right now of me using this outside just to show you how well it works. And yeah. Alright, so let's do the demo. This is the main LED. You can see pretty far with it, honestly. And there's no flickering, nothing, so that means the BMS is working. Now we have our red light. I mean, it's dim, but it still works. We have our blue light, a little bit brighter, and works really well. Now we have our white light. That one works amazingly. You can see all the rocks in front of me. And so now, we go through the fun test, which we couldn't do before. White, blue, and red. I mean, it looks just the same, but it looks pretty cool. So, yeah, I would consider this a success. So, alright, let's get back to the desk. So, it worked pretty well, as you can see. I'm very happy with this. I'm going to be bringing this to my school. And yeah, if you have any other project ideas, let me know. Because, I mean, rebuilding stuff like this is pretty fun. And yeah, I'll see you next Sunday. Thank you so much for watching. And you might be seeing some computers and how they deal with BBs. So, hope to see you there. Hello and welcome to Sealio's Projects. Today, I'm going to show you how to take a PC power supply and make it so it can work with balance chargers or really anything that's 12 volts. To start off, you might ask, why do we even need to make a power supply out of a computer power supply? Well, one of the main reasons is that these power supplies, since they don't have any fans, they heat up very quickly, and once they get hot, they stay hot. And when you're charging something very large, like lithium polymer batteries or really any battery, these things heat up very quickly, and so do these. And as you can see, there's only one plug on this. So what I've done with power supplies like these is you harvest the 12-volt connections on the motherboard and the 5-volt or 3-volt connections that are also on here, and you can take them to power fans and power the motherboard. Because, for example, this thing, the 12-volt outputs that it has can do 17 or 11 volts at 12 or 11 amps at 12 volts, which means that this is, I mean, granted this is a 240 watt power supply, but that means on a single rail I can have 170 or 140 volts, which is absolutely perfect for something like this, which is an only 80 watt charger. And this charger also can take a variable input, so this can do 11 to 18 volts, which means that this is perfect for something like this. So, the way how we're going to start this is we're going to first make sure that this thing is powered down, which thankfully it has a button on the side, or on the back, which presses it and discharges everything on the inside, which they don't really have that nowadays. To find which rails are which on here, because we know which ones are the 12 volts and we know which ones are the 5 volts, but we don't know which one can do more current. We're going to use something like this. This is a female 24-pin motherboard connector. So what this does is this pops right onto here, and it connects the two buttons, or the two lines right here. Every green line on a PC motherboard, or at least the green and the black wire, the green wire is to turn on the actual power supply. So when you take it and you short it using a switch, you can tell the power supply to turn on an output voltage even though it's not connected to a PC, which is also how some people daisy chain power supplies. It's not necessarily, it's perfectly fine to do so if it's just you're using it for 12 volts, but if you're daisy chaining it inside of a computer, there are much better ways to do it. So I'm gonna hook this up and we're gonna start doing some testing with the voltmeter. Thankfully, we know that on power supplies that are standard, this 4-pin or 8-pin connector sometimes will always have 12 volts because this powers the CPU and the fans, which means that we know for a fact that this runs on 12 volts because, well, they run on 12 volts. Now, thankfully, both of these run at an excess of 10 amps, which is perfect for an 80 watt power supply because, well, 12 times 10 is 120, so since these can both do more than 120 watts, we're perfectly fine. So what we're going to do is we're going to test both just to verify that nothing's wrong with this power supply, since this is an older power supply, and we're going to do that by using the switch. So as you can see with the light and the fan, it turns on. So it allows us to safely do that. Instead of jumping the wires, we have a full-on connection. So let's see. Will we get our wanted 12 volts? $11.8, so it's not exactly 12. And 11.8. So it's not exactly 12 volts, but thankfully in our case, this thing can still work at 11 volts. Most times the voltage will be closer to 12 volts. It's a little bit odd that it's 0.2 volts off, but when you're dealing with older power supplies, you get what you get. Beggars can't be choosers. So now that we have all this working, we're going to turn it off and unplug it. Now we're going to flip the switch just so that it discharges. You always got to make sure that it discharges, because if not, if I cut and solder and there happens to be a short, everything will spark and nobody will have a fun time. So, now that everything is discharged, I'm going to cut off the zip ties and the connectors and then solder the connectors to this, which actually, let's start this right now. We need this specific barrel plug due to the fact that, well, it plugs into the port on the power supply, on the charger. By the way, this is a balanced charger for LiPos. So we now have this. Now we're going to take them, we're going to strip them. Thankfully on the outside of this, it tells us the positive and negative of which terminal. So in other words, positive should be inside, negative should be outside. And sometimes the casing will always be the same, but the power might be different, or the polarity might be different. So you might have positive on the outside and negative on the inside, but the good thing with that is the wires still go to where they need to go, so you just have to change the color of the wires, or change which wire goes where. Oh, that came out beautifully. So the way we could test this is using our continuity function on our voltmeter. So we currently have positive. Now, if it registers on the outside, it means that we have outside positive, which means we have to then solder the positive to the negative. Okay, now let's test the inside. Okay, so this is showing that that positive is inside, which makes our life a lot easier because that means we could solder directly color to color. So now that we have all that done, we have this nicely stripped. We're gonna just twist the wires. Going to move this out of the way. And since everything is disconnected, we are all safe to cut. Ooh, that just went flying. We're gonna take the zip tie off too, just because it makes our life a lot easier. Now, as you can see, there's a fan on this power supply, because this this charger. And the reason why is this charger just heats up. So what I also can do, since this is a 12-volt fan, is hijack the other route and make it so it works. But I'm sort of gonna shy away from that because I do use a different charger with this. And actually, you know what? We'll do that still. But this doesn't require soldering because I made it so that the connectors come out. So now we have our 2 grounds and our 2 positives. So with that, what we're going to do is we're going to now take our positive and our 12 volts and our positive. We're going to spin them around all nice. And then we're going to take our soldering iron. Actually, you know what? No, first, let's solder each ground positive, because since it's discharged, I'm pretty much just soldering 2 wires together. Just so happens that they happen to be connected to a power supply. And I'm going to be using electrical tape to seal them up just because I don't have heat shrink, which I probably should buy some. So let's get this all nice and soldered. Now that we have the 2 things soldered, we're going to now wrap it up in electrical tape just to make sure that it does not short, because even while we're testing it, we don't want to short, because while these power supplies do have setbacks, they can still always cause a fire. We now have the ends soldered, and they're both a good few layers away from each other. So we're gonna plug that in. We're gonna plug this power supply in, and with this power supply plugged in, we'll be able to test it and make sure that this turns on. Because if not, then we got a problem. We have it plugged in, and we should see it turn on. There we go. We have success. So you can see how easy that was. We cut 2 wires, solder them to a barrel plug, and that's it. So now I have a power supply that's not going to heat up, that's going to be silent, and while it takes up some more space, it's overall a lot safer, because these types of power supplies can easily overheat, and since they're in a plastic housing, they can melt. So now that we got that done pretty quickly, we're now going to get this fan to work so that this still stays cold. Now thankfully, the wires that I used and the connections that I used were from crimp sets. The only thing is though, my crimp set is upstairs and I'm not gonna go grab it, so we're just gonna smush them. And now first we want to take these little housings and pop them on there, because with these housings it'll make it so that when the 2 crimps are together, I don't have to be afraid of them at all. What do you call it? Smushing. I'm gonna get that in. And you know what? We're actually gonna be safe. We're gonna turn off the thing while we're working. I realized I should have done that a while back. So now we're just gonna continue smushing them. Now, due to the fact that I want this to be very safe, I'm also going to put a little bit of solder on the wires and the connectors. This will make it so that if I have to pull really hard, the connector is not going to come off, because that has happened a few times. And it's really just that easy. So now, ooh, that's very warm. So now we're going to do it on the other one. We're going to repeat the same process. Sleeve. Come on. Sleeve. Crimp. And solder. So now we have the sleeves on, and well, we're just waiting for that one to cool off because I almost burned myself. And once the sleeve is on that, we can just plug it straight in because we know which one's positive, which one's ground, and make sure that the fan works. And if that does work, then we're gonna charge this 6S 5000 milliamp hour, I think it is, or 3000. Forgot which one. I think it's actually 3000. And yeah, and that's it. All right, let's test it. The fan works. I don't know if you can actually see it, but the fan is spinning, so we do have success. So now we have a fan in this power supply and a fan on this, which means that the next thing we need to do is actually charge a battery to make sure that this does work. So let's take this. Okay then. It just turned off. Let's turn it back on. You know what? For safety, since I do have to move some stuff around, I'm going to wrap this up in tape. Good. Normally I have it exposed because I have them using different types of connectors, but let's just be safe. So, stop making noise. The fan got caught off on it. So we take the positive to positive, negative to negative. We plug in this. Now I'm fairly sure this thing is fully charged, but it's always safe to keep your batteries nice and charged. And this particular connector this particular charger can do up to 6S batteries and pretty much any other type of battery, which is absolutely awesome. So let's put this up to the max current possible, 6 amps, which this thing won't charge at 6 amps just because of the total wattage. It literally can't. So alright, so there we go. You can see right there, it is in fact charging. It's currently charging at 2 amps, 24 volts. Now that's just because, well, this is rated for 80 watts, but it doesn't mean it's going to use that 80 watts. I found that out very, very quickly. But also it makes sense. If I'm doing 25 volts, the most I can do is about 50 and a little bit, so that's like 2.5 watts or 2.5 amps if I'm doing 25.2 volts. So I mean, that was quick math, but that's definitely wrong. But overall, as you can see, it works. And now I could easily go and work on something else and say, okay, this is not going to heat up. I'm not afraid about that. This is not going to heat up, so I'm not afraid about that. And this is a very expensive, I think it was like $60 to $70 charger. So this isn't going to heat, this isn't going to explode. This might heat up and melt. Let's turn that off, actually. And that's it. So, and another thing is also, since this does so much, I can take the stuff that comes out of this and I can use it for other stuff. Or I can charge multiple batteries at the same time, as long as the amperage is not messing around, or as long as the wattage is not too crazy. So, because one of these wires can do 110 volts max, or 110 volts maximum, and the other one can do 170 watts maximum. I hope I said watts for that one. And so what that means is I can charge one thing on one side and the other thing on the other side. And since this has a fan built in, it's never gonna get warm. And if it does get a little bit warm, then I'm still fine. So this is gonna charge, as you can see, It might take a little while, I don't know, but overall, I consider this a success, and it shows how easy you yourself can do it. So, thank you so much for watching. This is actually the first video I'm trying a second angle to show the type of soldering and stuff that I do. I really hope you enjoy it, and I'll see you in the next video, next Sunday, 8 a.m., as per usual. Bye! Hello, welcome to Sealio's Projects. Today I'm going to show you why this oscilloscope that I pulled from the garbage is really awesome. So, to start off, this is a Tektronix TDS-460A. It was made in the late 90s, and it has a dot matrix screen, which we'll get to later. But to start off, this I pulled from the garbage. This was just laying out, ready to be recycled, and thankfully the person who was about to throw it out let me take it home. So I use this a bunch of times. It's fully functional. I actually have bought some expansion cards for this, which I'll show you later. But to start off, let's just turn it on. Now, I don't know if you'll be able to hear it, but when it turns on, since this is such an old model, it actually has a fan built in. This is effectively a small computer, and it's really cool. You'll see why we have this monitor in a few minutes, and I can tell you it's still usable today, but you would have to spend quite a bit of money to connect it to any actual computer. So it's going to take a while to boot up, and then once it boots up, you should be able to hear a few clicking noises, which are the actual relays on the inside of them. And we'll actually get to hopefully look at those relays if we can find them inside of here. Those were the relays. Well, one of the cool things, which I'll show you right now, is that this has a built-in video expansion port. So, as you can see, if you can't see it on here, you can see it on here. So as you can see here, obviously the date and time is fairly incorrect. That's probably the last time they used it. It has just a normal dot matrix screen, and it's funny because that dot matrix is actually shown on here. But if we were to go and use a signal generator, which we have right here, or function generator, we can go and take the signal and actually capture it on something like this, which, using a VGA to HDMI capture card, we should be able to capture. So right now what we're going to do is we're going to hook up one of our signal probes, and we are going to go and see what this looks like on the actual dot matrix screen. So right now we have it hooked up because I had to test it before I started filming. I'm going to turn it on, and so it's currently set to a, this wants to actually stay up, there you go, that fell off. Come on. So this is set to a 10,000 kilohertz sine wave, or sorry, 100,000 kilohertz sine wave, or 1,000 hertz sine wave. So I just pressed the auto set function, which should allow us to easily see. Okay, so now we're seeing a waveform, and now we just need to hone it in. It's not the prettiest, but it's something. Now this is not a very expensive signal generator, so it's not going to look the greatest. So that was the sine wave. Now let's see what it looks like for a square wave. As you can see, it's not the greatest, and I don't exactly remember how to make it look a huge amount better, specifically with this oscilloscope. So here you can see we have a triangle wave at the 100,000 hertz, and it's reading it pretty well. It's reading it well within the range. It's reading it from, let's actually see, measure. And as you can see, it has all these different functions on it. High and low. So I sort of messed up this part. What you're going to see is that the voltage high is 260 millivolts and the voltage low is 240 millivolts. And the good part about this is that it's reading a positive and negative absolute value, and that's really helpful because it means that it's actually reading the signal generator correctly. If the cell high was too much, in other words, it was 500 millivolts with a negative 240 millivolt low, it means that the total positive and total negative are out of range. The range is supposed to be set to 260 millivolts, so having it be within that range is really good. I really messed up trying to explain this here, so this is just me recording this while editing. Alright, so now that we see that it has captured the high, which 260 millivolts, and low, negative 240 millivolts, we're going to see what's actually inside of this type of machine. So now that we have these screws out, I'm just going to show you, before we take this thing apart, what actually would come with this Tektronix for TDS460A. So to start off, we have software for it. This is scope data management software. Don't know, I haven't really used it yet. I've only used the Wavestar, which is what you actually use it with. And then, sorry, I almost just dropped that. Another thing, but on 5 1/4 inch floppy, which I have yet to test that just because I don't have something that can read 5 1/4 inch. I have an adapter that can read normal stuff, but not 5 1/4 inch. Some, it looks like plastic baggies or latex baggies. I don't know what material these are. For it looks like either floppy drives or just hard disk drives, which you don't think, well, you can't put a hard disk drive in here. Well, it actually has one inside of it already. It comes with DocuWave software tutorial. Comes with instructions on how to use the probes. Well, it looks like it's just a thank you for the Tektronix stuff. More instructions. And this, which is the actual software that you would use with one of the expansion cards back here to actually go and look at the software. So it comes with, this I think is just an extra random floppy disk, but these two are the actual Wavestar software. In other words, this is what you would connect to your computer so that you could actually connect this to your computer and work with it, which it's pretty cool. I have done it before, but I had to give the cord back because the cord was $3,000. So yeah, and unless I plan to solder one, which there's like 18 different things on here, and it's a GPIB port, I don't think I'm gonna be able to connect to this. So let's take this off and put it to the side temporarily. Let's take these screws, put them in my pocket so we don't lose them, and let's take this and let's move you to a different angle. All right, so we're now at a different angle. We're gonna take this thing apart. So first, we slide off the back plate because we took out all the screws. Then that allows us to slide out this leather pouch, which I do have to say, it's very nice, and I do love the color. Most of these that you find don't have the leather pouch still on them because they're either cut, torn, or they just don't have them. So now, this carrying bar, we're gonna take this, we're gonna flip it up so that we can take out this screw. Thankfully, all the screws on the outside utilize the same screwdriver, which is a T15 bit. So, knock that one out. There you go, and we push it out forwards. Now, by the way, in the meantime, I actually did discharge this. I just wanted to say that. So as you can see, none of the relays are done. They're clicking. So, it is warm though. Here, let's put it on its face for a quick second. There you go. And just a look at it from here. So that is a cathode ray tube with, I have no clue that's a vacuum tube or not. It sort of looks like it, but all I know is that this is cathode ray because some of the stuff actually says on here, emergency don't use. So specifically, which I find really cool, right there, it actually says that all of the X-ray rays are actually sufficiently shielded. So that's why I'm not going to be taking this any more apart than just showing, hey, look, this is what's in here. We have a 2-watt fan, a 12 volt, 0.16 amp fan. We have the, what do you call it? We have the projection screen, and the cathode ray tube, a bunch of internal electronics. I'm trying to see anything more interesting. No, not necessarily. So now we get to the cool part. So So here are the expansion cards. Let's actually take this out. Now, I will admit that this did not come with all of the expansion cards in here. It actually only came with one, which was the one that's needed for the thing to actually function in the first place. So, this one is the graphics card, which, I mean, it is technically a graphics card since it outputs 2 graphics. And let's just quickly pop it out, just make sure we're not connected to anything else. You know what? It's connected to 5 different things, so I'm just gonna pop you off, and I'm gonna show you what it looks like. So, as you can see inside there, if you can see inside there, come on, focus. It's just a bunch of hand soldered, or maybe not hand soldered, but soldered on boards, nothing really interesting, no relays, nothing. And that is what it outputs. It just has VGA. So actually, something that's really cool, which I'll temporarily pop this back on, is that it actually tells you exactly what you need. So as you can see, it tells you exactly video, GPIB, which this is the really expensive one that I would have to spend about $3,000 for a GPIB to USB cord, RS-232 port, and a printer port, which it says electronics compatible, but when you go and look, it's just all printers. So the one thing that came with the 2 cards, which is this one, which I'm pretty sure is just a computational card, which allows you to do more math, which it did come from college, so I'm not surprised. Also, here's just a quick view of the back side. A heck of a lot of stuff. And the weird thing is, right there, that's an IDE 40-pin connector. I know, because I was able to use one of my cords to connect certain stuff. I also have no clue what that is, this main part right there, but it's a mystery that we'll never know. So the 2 cards so these 2 cards actually came with it. All these 3 did not. So I bought the RS-232 port, the RS-232 card, to see if I could get it to function, which that also came with the printer port. And as you can see, these use EISA, or extended ISA ports, which I actually do have a DC to DC adapter, but I'm way too afraid to plug it into here because I don't want to brick this thing. I mean, you can actually see how damaged some of these things are. I mean, look at that. The FET is literally at an angle. So, yeah, I mean, they're not really interesting. They're standard cards, but for me, it's pretty cool being able to actually add more to your already functioning oscilloscope. And they have these batteries, which surprisingly still work. They actually are able to maintain the same date and time. So that's really it for the internals of this thing. It's more just old tech, nothing really crazy. But I actually will mention one thing, because I know this from certain smoke detectors. I am 95% sure that that is what creates the x-rays. That tube right there, that plastic tube right there, because it's shielded in a specific way away from everything else. So, yeah, and I'm sorry if the audio is weird. The microphone is pointed at the thing. So, let's now go and talk about why I love this type of stuff and why you should go for these types of machines instead of the newer types. So while this is a older model of oscilloscope, and it still does function, you might say, well, why should I buy it? I could get a new oscilloscope for $300 and it would function perfectly fine, and I would have literally 0 problems, and it comes with the most updated stuff. And that is true. I was thinking myself about buying an oscilloscope. But the main thing is, this was free. This was pulled from the garbage. This taught me how to use oscilloscopes. Now, I did learn in school how to use oscilloscopes, but this showed me what you really can and can't do with oscilloscopes. And that's sort of why I love old tech like this. It's old. This thing, it's been working since the 90s. This is almost 30 years old. And everything still works in here. Meanwhile, new stuff nowadays, if you don't software update it, it can sometimes break itself. So, it just, this tech, it's made perfect. It was made, I don't want to say with love, but it was made back at a time where you needed super reliable stuff to work. And if you didn't get it to work, well, you were out of luck. So that's why I love tech like this. You get to save and reuse tech that people don't need. Like for example, my school throws out a lot of technology just because it's old. Sometimes it's not functional, but majority of the time it's just old. And the problem with that is, there are certain people like me who would happily want to take this tech because I don't have stuff of my own. My power supply I got from the school because it was broken and wouldn't go back together. So I took it, I fixed it, and for some reason this doesn't want to go in. So getting back to what I was saying. This type of tech, it's old, but it functions. And most times it's free. If you go to your local workshop or your local whoever and say, hey, I want to do some stuff, I can't afford an oscilloscope right now, or I can't afford a power supply right now, they definitely have these types of things. And they might be willing just to give them to you for free. Because it's old tech that nobody uses anymore. But if you can find a use for it, it's really awesome. I mean, I have some really old stuff that I still use to this day. Old tech, like for example, the 3200XS, an old computer. I use it for testing old stuff and old hardware. And I actually use it to connect to certain stuff like this. So, in other words, to end this all, if you like old tech and you don't mind using old tech, you just care about the functionality, these types of things, old oscilloscopes, old tools, old everything, are perfect for you. So I would suggest, go find someone who has old tech and say, hey, can I borrow this? And they'll probably say yes. So I'm looking at this after editing it, and I realized that I talked way too much, saying the same things over and over, so I just cut that little bit out and brought it all the way to the end. So if you're still watching, thank you so much. And now back to me in the past. While I'm screwing this in, I'm gonna wish you a good week, and I will see you next Sunday, 8 a.m. usual time. Thank you so much for watching. Have a good day. Hello and welcome to Sealio's Projects. Today I'm going to talk about something very near and dear to both my heart and my wallet, which is the battery that goes to my e-bike. This battery is exceptionally safe. It has 2 fallback systems and technically a third. So to start off with, we have an active balancer. Now, I had this on because the flashing light goes on a lot. An active balancer goes and makes sure that the voltages of the individual cell packs are the same. Now, it depends on how much, like you can have it set to 1,000th of a volt off or 100th of a volt off. Personally, I like to set it to 100th because it allows for some wiggle room. Now, this is a 14S balancer because this is a 14S 4P battery and it uses 21700 cells and it is 1 kilowatt hour or 1008 watt hours. The 8 just gets thrown away. And yeah, so this is for 14 cells. So now this works perfectly. This is also a Bluetooth module. So in other words, I can use an app, which I'll show right here-ish, that actually shows the cell voltages whenever I want. I just have to connect to the app, which is very helpful. And since this thing does not turn off, unless I make it turn off, it will always be broadcasting the voltages. So I can always go and check to see if I need to charge them or not. So this was, I think, about $50-ish. It's a very good company. I'm fairly sure it's the same one that Daly makes, D-A-L-Y. Daly, I don't really like a huge amount just because a lot of their stuff breaks and their customer support is garbage. But this thing pretty much makes it so that when I'm discharging or charging, the cells never get too far out of whack, which, since this is technically only a year old and the cells are acting a little bit finicky just because the fact that, well, I haven't used it in 2 or 3 months. This is really useful because it keeps everything within range safely without having to do a whole lot of intervention. You just got to solder a lot more wires, which this little thing right here is the wires. It uses a JST PHR 15 connector, which just means 14 and 1. And yeah, now this I will also just start and say, this thing right here, this is so I can control the LEDs on my bike. This does not have any anything related to the battery. I just put it on the battery. That's it. I mean, you could literally see it's literally just an LED thing. So now we get to the back. Now this does not look as nice, but here is where the BMS is located. It's a 14S 30 amp discharge BMS, so it's able to do quite a bit. I personally don't discharge from the BMS just because with my bike it can do well over a few hundred amps. Like I have a 1,000-watt motor and I have a power supply, or I have a motor controller that can easily do well over 1,000 amps if you push it. Well, no, not 1,000 amps, 1,000 watts. So this BMS is very important because it allows me to charge the cells without having to worry that they're going to charge out of whack. Like if you just charge it by plugging it into the battery itself, you could have cells that go up to 4.5 volts, which they shouldn't. They should stop at 4.25 for safety. And you could have other cells that are 3.5 volts, which that actually almost happened to me, but thankfully I had both the active balancer and the BMS. The only problem with this BMS is that it charges up to 4.1 volts, which it's not the greatest, but you still do lose out on a volt and a little bit more. But honestly, being able to confidently charge this thing with either a dumb charger or a smart charger, dumb versus smart being where it just constantly puts out a certain voltage until it drops a little bit, and then the other one, a smart one showing like temperature, has a fan built in and all this other stuff. The dumb chargers can usually be about $30. The smart chargers, which I'll put a photo of the one that I have here, can be sometimes $60 to $70, maybe $80. The one that I have is $80, which is not cheap, but you're paying for something that's never gonna overheat because it has a fan built in and it's super safe and it's gone through a lot of quality control checks. So those are the two active and passive systems on here that keep this thing safe. And now for the thing itself. Now I'll find photos of the cells just because I don't want to take this apart because I made it so that it doesn't get taken apart. But inside here are 21700 Samsung cells. They are very high quality. They're about, at this point, I think $750 a pop per cell. So this is not a cheap battery to say the least, but this is rated for 100 amps total discharge. It has 4 strips of nickel plating on each of the serial connections. So pretty much that means that I can discharge at most, nominal voltage is about 50.7 volts. So at nominal voltage, I can do, if it's rated for 100 amps, I could do 5,000 amps, technically. Not realistically, because at such a low voltage, I'm gonna have to draw a lot more, or it wouldn't work as well, but this thing is rated for constant usage at anything below 100 amps, which is amazing. And technically, I have done 100 amps on this in testing. Granted, it drained the batteries instantly, which makes sense. But this thing is it's beefy, it's made to work on anything, and since these cell wires right here, you can just take and pull out, I'm able to individually test any of the cells and individually charge them if necessary. Like if one cell gets out of whack and I need to get home, I can just use a 4.2 volt charger and just charge off of it. So, all good. So that's the electrical systems. Now, this also is very good, or it's very safe, because of physical systems, just systems that I designed it so it works really well. So to start off with, this plate right here, it's a fairly thick plate. This is what keeps the actual cells in the battery, or in the housing. This is also made out of PLA, plastic, so it's gonna take a long time for it to decompose, and it's also going to be fairly strong. It has the rigidity of ABS, but also it's a little bit bendy like TPU. So, I mean, granted, it's just PLA, but it's strong and it's not going to just shatter on impact. So we have that to start off with, and it goes the entire length of the battery and has 4 screws to hold it in. So it would take a lot for both screws to fall out, or for all the screws to fall out and for this thing to fall apart. We also have, the housing is made out of PLA. I used a 0.8 millimeter nozzle to go through this pretty quickly, and the way how it's printed is it's printed in pretty much, it's printed like this. Obviously it's two different prints, but it's printed like this so that it's not going to shear out from the middle. It has to shear out like this. And when you have the battery sitting like this, if it shears out, it's not going to be able to, like, the entire thing would have to crack open like an egg, which is not physically possible because of the fact that my bike has two security rails to also reinforce the frame. So that's another thing. I also, in the cracks that I took, because I printed it, as you can see here, with pretty much a zigzag motion in it, it's not going to be able to fall apart in, what do you call it? Yeah, it's not going to be able to fall apart as easily. It's not just going to slide clean off. Like, it actually has to bend apart. I'd also, if you look at the crack that's there, there's glue in there. Now, there's a mixture of super glue and crazy glue, super glue and hot glue. So the crazy glue, or the super glue, is meant to actually hold the thing together, and the hot glue is just to keep it insulated. So realistically, if I took this and I put it through a rainstorm, which I never would advise you do if you're going with a DIY battery, unless it's very secured. This is outside of its normal container. Like, this gets on my bike and then this thing gets covered. But this thing is very impertinent. It won't get affected by water. The only way that it could get affected by water is if water gets in here, but this place is fully closed off once it goes on my bike. It's fully shielded and it's fully enclosed. And I also replace the tape every so often. So, yeah, I mean, I just wanted to make this video just to show off this battery and just to put it on the record that I built one, because my school just released a rule pretty much saying as long as you're not an idiot with your electric bikes, you can have it on campus, which that was something that I was afraid of not being able to do. And yeah, so I'm very happy that I get to use my electric bike on campus, and Walmart Special will get to see another day. So thank you so much for watching. If you have any questions about like what type of stuff you should buy, put it in the comments, and yeah, have fun. I'll see you next Sunday, 8 a.m., the usual time. Bye.